I'm very grateful for the invite to come and talk to you today, but I also want to say that a really key thing for me in my role in MOD is I'm really grateful for the input of signal processing into the areas that we need it, and I think you'll see that. So I'm really key that a key thing for you to do for us is to give us the cutting edge ability, and that's what I'm going to try and bring out in the talk. I'm a portfolio commissioner. I'm not going to take you through organisational design and what that means. What I'll try and land for you is, in a sense, I sit between those military users that we heard from yesterday who have very important needs. I sit between there and the scientists to try and create the right opportunities to procure the right science to give our military the cutting edge that they need. Before I zoom on, I think Mike was curious by my title, so I'll have a go at explaining the title. Two strands to the title, really, for me. The first strand is information generator. Signal processing, although fascinating and interesting as an academic subject, for me, it's about generating information from data. We need information to make, as the military advisors said yesterday, better decisions, be that for strike, for using force, for thinking, for procurement, or even recruiting better personnel into the military. We need to generate the right information from everything that we understand. So for me, everything that you guys are doing or contributing is to be part of a machine that I call the information generator. The machine is contributed to by the signal processing, and for me, things like the data, they are the fuel, they are the input that goes in one side, and out of that comes information. And if you remember the MA's talk yesterday, they talked about a triangular pyramid. We go on from information to generate intelligence and action. But the first thing that you guys really plug into is that translation between data and information. Keeping the lights on, what's that about? Well, there's an obvious fear factor there in terms of does the generator work? I don't want to paint a worrying picture, but frankly, we can't always keep the lights on. We can't always see into the places we want to see with our sense in, and our signal processing is not always adequate to give us what we need from the volumes of data we have. So I'm going to paint you a picture of what that really means. But keeping the lights on for me is letting the military be able to see into the places, have that light to be able to see what they need to make the military decisions. And I really want to start off with a scenario, really, which is to look at this picture. And we're thinking about this military person on a ship. We're looking at a display. We're looking at the fact that this person is being fed data in real time. This data could be threats to the platform. This data could be the fact that in 5 seconds a missile is going to be piling into the side of the ship. This could be that critical. So we're talking about very difficult environments. The future operating environment is contested. There are going to be many challenges to that signal area. We're talking about the fact there's going to be radars, there's going to be electro-optic sensors. We're going to be working, we heard it yesterday, there's 5 domains that we work in. We work in the maritime, the land, the air. We work in space. And the 5th one that you heard and was opened up in questioning is the cyber electromagnetic environment as our 5th domain. We're going to be working against more difficult targets than ever, coming quickly, making busy decisions. Some of these systems that we currently have many air gaps. We have many different systems for different sensors. We have different screens. We have interesting ideas like whistles or people telling each other about who's in charge and what the threat is. This is the difficult environment that your signal processing needs to be plugged into. We need reliable information exploited forward by the military in real time. This is traditional, though, in a way. This is something you would have heard my military colleagues say for a while. And this isn't a sci-fi picture. My son might like this picture, but this is a picture that we paint in the military. This is where we would expect to be fighting future battles, and that's what we're being ready for. We're looking at the urban city, we're looking at canyons, we're looking at blocked areas, we're looking at wanting to know what's going on in every one of those buildings. That is the problem that we want to sense, as well as what I would think from my radar background, relatively easy air targets, which are frankly not as difficult as that problem. So that's the kind of problem I'd like to point you towards, the congested, the contested environment. What else do I want to paint a picture of? I want to paint a picture like this. Always hard to get a high-resolution picture of what the military get up to in these HQs, and this is about the highest resolution I wanted to get. So this is what an HQ looks like. So when you're talking about iStar, when you're talking about sensing and bringing information together, what does it end up being? You end up with an HQ that's something like this, with loads of people on laptops forming intelligence and different parts of the picture and trying to inform what the next decisions might be. What do I think of when I look at that? I think of stovepipe hierarchical decision making. I think about lots of reporting. I think about lots of humans, literally hundreds of humans. I'm thinking about slow battle rhythm. I'm thinking about out-of-date intelligence. I'm thinking about when the aircraft will next go forward and will it be relevant. But that is how we are ready to fight wars in certain ways at the moment in terms of where your signal processing would feed into in intelligence. So what are the challenges? I'm laying open at the beginning what the military perspective is. I'm now going to change direction, talk about what some of the sensor challenges are, and then start to point to you towards some of the examples that I can share today with you. So these are some of the things that are really on my mind, and we heard a good number of them yesterday. Sensor systems, they need to be connected, agile, affordable. What does that really mean to me? It might not be big aircraft anymore. It might not be exquisite satellites or something else. It might be just a deluge of lower cost, affordable sensors that are networked in an agile way quickly on the battlefield. But the key thing I do want to say about sensors is that sensors and the hardware is not a solved science. We still need better sensors because we cannot see where we want to see. The hardware isn't there yet. Some of the sensors maybe to point to as an example for you, we're looking at things like quantum gradiometry, we're looking at muons, we're looking at all sorts of other sensors to unwrap that problem of that city, that future challenging environment. What do I think about detection? I think we've heard a lot about detection. We've heard a lot about different optimization techniques already. But things like range, noise, clutter, that's really hard. Free barrier is absolutely key to me. Seeing an air target, if I keep picking on that one, relatively easy. We can do RCS calculations and point beams in different directions. I want to know what's going on in this room if I was up in the sky. I want to see and hear who's in here, what equipment's in here, without placing any equipment in the room. That's my challenge. I want to see what's going on inside. I want to see what's behind walls. I want to see people. I want to see critical targets. And I want to see critical items. That's the kind of environment that we're into, really difficult detection. Resilience, I can't remember, there's a question from this side of the room. Resilience means a lot for our military. They need to have, as you heard yesterday, assured, predictable performance. But the other thing that we need to have is that the enemy are not allowing us. We heard Hughes talk yesterday how was bistatic SAR used against bistatic radar used against us in the Second World War. We're not in an uncontested environment. The enemy will be jamming us. The sensors will either be damaged or at the time jammed to not work. And there's certain other ways, as you'd imagine, that we would not be able to have the freedom we want to. Autonomy is both a enabler, but it's also got potential risks in terms of counter autonomy and what would happen with different algorithms. Operating environment, I've told you already about the urban. I won't focus on that. The one I want to focus on, those blurred boundaries. The fact that you could say that there's a war going on in Syria, or there's a battle in Afghanistan, or there's an Iraq. In the future, that boundary between which rules of engagement we're under, where is war and where is not war, where is conflict, will be completely blurred. We will not always have that ability, frankly, to be in UK mainland and say this isn't war here and the war is over there. Where war will be, it will be potentially across the whole of cyber, the whole of the electromagnetic environment, and the rules will be blurred as to where war is occurring, where the engagement is. So the operating environment is not just difficult in terms of seeing inside buildings, but the operating environment is difficult in that we will be fighting both in the electromagnetic cyber world, in the real world, here, and everywhere else, and that's challenging. But what the signal processing is really for me is, if I come back to the point I'm centre on, is that data into information. We can collect data, we can have sensors, but the key thing we need to do is to get your signal processing to get us to information. And then we need to be able to know that information, how it was collected, the legalities of that, and that will impact how we can use that, how we can fuse it, how that can go into different sources. But that's a kind of whistle-stop tour of some of the science capabilities that I would say I'm worried about in this area. What's the mission? Why do we, Ministry of Defence, therefore, invest in sensing? That's the mission, if you like. And I think there's a key word I want to unpack here for you. We want to ensure sensor overmatch for near-peer state threat for intelligence, platform survivability, and weapons. There's a lot of really important words in there, so I want to break those down for you. What does overmatch mean? That means we need to be better. We need to be better than everyone else. We need to be able to see further, see better, see more clearly. It doesn't mean that I want our sensors to be as good as the enemy's, because I want ours to work at a longer range and to give us abilities they do not have. So overmatch is absolutely essential. Near-peer state threat means that in relative terms, more recently, the kind of nations that we've been going against, they haven't had the sophisticated abilities that we would expect a near-peer, so that's a country that would have the same kind of abilities as us, to actually impose on us. They will not let us have the freedom of operation in the electromagnetic spectrum. They will be jamming, they'll be confusing, they'll be taking out GPS, they'll be taking out all sorts of things. So the idea, for example, GPS will provide the time and synchronization to let something occur. No, there won't be GPS, let's just assume there won't be. That's where we need to start from, because it won't be that easy. And I think the last 3 points really there are we need to be forming the information, we need to be forming the intelligence. Platform survivability is, and I heard some good talks yesterday about a poster about radar warners. We need to do the right signal processing so our platforms can go, have effect, and come back. And obviously weapons is a key part of signal processing as well. So, this is my only slide that goes anywhere near your worry point about DST and DSTL and what's all that about, Mike. So DST, I work for the Chief Scientific Advisor's Office, so the Directorate of Science and Technology in Main Building. Main Building is about half a mile down the road. Hopefully you've all seen it or been there. It is the key area for science and technology where we lead on the strategy, we lead on engaging with the military users, and we come up with what are the strategic focuses for where science should be. Hopefully you would have seen that the science and technology strategy was published by our minister a couple of weeks ago. And from that, we have to make the difficult decisions. What areas should we invest in? How should we had a question yesterday about how should we balance between sensing, signal processing, information, and all that kind of stuff. This is where the difficult decisions are done, and we do that in conjunction with the senior military for what should we do the balancing. So my role in DST with my peers is to be the commissioner, the person who actually creates the opportunities and purchases the research. DSTL, who got an excellent representation here this week, are leading on the delivery. It's their job to give me the deep understanding of the science and what's possible, and for them and us to work, hopefully from Mike's point of view, not having to worry what the difference is, but DSTL will lead on the delivery. We work internationally by design, and that means that we work with our international peers as default, because that's how we would probably fight, if I'm frank, in the future. It is almost certain. And we are investing in all the S&T that we both need for our battle-winning edge, but also investing in those capabilities that we believe will make the difference in the future. So if you like things like quantum, we're investing heavily in quantum sensing because we're not going to deploy that on the battlefield now, but we think we need to know it. We're investigating quantum computing, all those kind of things. Absolutely investing in those things that we think are strategically important. What's our approach? The reason I want to put our approach in is that we want to confess, in a sense, that because we've been focused on many conflicts recently, we got a bit short-focused in our perspective. So our focus in the future is to do more driving, fundamental, game-changing research. Think of that word overmatch. We want to be better, and we want to be winning. We don't just want the second decimal SNR on some detection going up. We want to be fundamentally better, doing something much better than the enemy. So we want to focus on speculative, high achievement risk that will give us the higher reward. We want to focus on the strategic. We want to really be helping our users, but we want to be taking more risk is the message for you. We want to be able to work out how to get things like your signal processing and to pull that through much more quickly, to apply it, to understand how useful that is. That's where we want to go in the future. So signal processing in defence. I think Paul did a great job of taking us through doctrine yesterday. I chickened taking them through every paper, so I kind of cheated and jumped in here. What I'd like to position for you is that Military action fits into many different doctrine models, but if we think about the joint action that the military advisors took us to yesterday, the future force concept, I really want to focus on the military. We can use nice words, but it kind of fits into these 5 boxes on the right, and we can capture key things on the little words like fires. But the one that you guys actually contribute to with the signal processing, how I'm going to focus today, is really on the bottom right, the information activities. What are we doing to inform decisions for the information activities? So having given you an introduction about what is important on MOD, hopefully I've given you a picture that from our perspective in MOD, sensing is not solved. We're not assured to win it in the future, and there's a lot to do to get that overmatch. I'm going to take you through a few examples now that go across the sensor world of the kind of things that we've been doing. I've probably got too many examples, was my reflection when I was thinking about it, and that's what everyone kept telling me. But I wanted to show you at this level of classification a breadth of the kind of things to try and illustrate the signal processing picture of the kind of things that we're involved in. So I'm going to take you through those 6 with a couple of slides on each. I'm going to try and keep your mind focused on the fact this is about the military benefit of doing the signal processing. So what's the first one? Many of you have probably been involved or heard about Sapient. So Sapient is my, I'm going to start in the multi-sensor exploitation. We're thinking about how do sensors come together. What's my key message on here before I delve in? Well, my key message, one of my key messages here for you is open data standards, open architectures, and that kind of thing. But where do we start? We start in the top left. We have a deluge of data, and we often have a human in the loop who might actually be the person who has to process that. The amount of data that we might have in different ways, either in this scenario or others, can be overwhelming. We've heard reports this week about what's been put in the public domain about terrorist activities. When we have a data and we can't fully exploit it, what can be the consequence? Here we're thinking about how do we rely on the human being to detect. So what we did in Sapient and what we have achieved was shown in this right-hand architecture, if you like, and that was to create these 2, let's try the laser out, these 2 boxes. We tried 2 things. One of them was to come up with the automatic sensor modules, sensors that would be autonomous in how they execute their own functions, and they could then plug in an open standard way into a higher level decision-making modules. So this was trying to demonstrate many things, but for me it was about demonstrating the autonomy, it was about demonstrating reduced operator burden. It was also about flexible and reconfigurable. We don't know what that city will look like or where we need to put sensors or where we need to go. So we need to be able to plug and play in open standards with non-proprietary constraints on us, all sorts of different sensors. We want to be able to fill the battle space, if you like, with these kind of complementary sensors. And what we need to be able to do with those sensors as well, the key phrase on the bottom left there, is that we need to get from sense in to information. So even in something like this where we might have radars, optical cameras and everything else, we need to get to the information. We need to get that information to the user in a usable time frame. So what do we do? I'm not going to take you through the deep aspects of it, but there's 2 use cases here, and I think we touched on them a bit yesterday. Within the higher level module, that's the one that connects them together. We have had different approaches, like Bayesian said here, but different ways of actually searching, tasking, and bringing together the fusion of the data. But in the sensor level, the bottom one, we've looked at different ways of actually letting the sensors work out how to point, work out where we want to see, work out where to put their areas of visibility, which areas they want to illuminate. And I think one of the interesting things in there is one of the words that Paul picked up on yesterday that I'll go for as well, trust. An absolute key thing in this data stream for me is how do we get the data to flow in a system like this, and we can trust it both from the reliability of detection, but also trust it from a military effect point of view, that they know that they could act on it because it will satisfy that key word that we heard, which was the legal requirements to know how the information was derived. 2 use cases that we did here is base protections. That's probably the easiest starting form of doing that urban city, and how we're able to have networks of sensors demonstrated. There are other examples, but also the counter UAVs. That's the fact the UAVs are so cheap and prevalent. That's a massive threat as well as an opportunity. And how can we perform missions against those with a sensor network? What do I think the future looks like then of something like that multi-sensor exploitation? I think the idea of putting up a really expensive wide-bodied aircraft sensor is probably, it's good. It's maybe good for the standing off a few hundred miles kind of warfare. But I think the real reality is that we're probably, and I've seen I saw a sneak preview of the next talk video, it'll look like that. I think it's going to be swarms of sensors, either on the ground or otherwise, automatically forming networks that actually support the soldier in their decision making. So a big theme for us that we're looking at as we're reviewing our investment at the moment is how do we do distributed sensing and fusion, and how can we make that work where the cost of the sensor is probably not the dominant item. And the key enabler of that this slide's out of date because it says the task is about to start, but the task has started under UDRC. One thing that we need to be able to do is to, when having those distributed sensors, make them form up into an ad hoc network automatically and to be able to work in that network. So I think this is an example, if you like. I like the fact that within this slide, we highlight the fact that I, as a military person, want that automatic network that's going to create itself. But we need to actually do detailed work in your expertise from the mathematical modelling through the kind of simulation. But then the key thing, and I think an absolutely key thing that I would highlight in some of the talks and posters we saw yesterday, is to make sure we get to real-world verification. And I think that's somewhere where my DSTL colleagues can really help that to occur. And this is an example where we're looking at electronic surveillance sensors to support the soldier when they're in difficult future environments. So that's what I think in one of my visions as to where signal processing will go. One of the next area I want to go to is electronic warfare as an example. I want to show what will be happening in this space. And I've seen some really good examples yesterday. I saw it with one of the posters on radar warners. Electronic warfare, so what's this all about? Let me give you the gentle start. Electronic warfare for us, it's electronic defense, it's electronic attack, and it's electronic surveillance. So we want to be able to attack in the EM spectrum, we want to defend ourselves in the electromagnetic spectrum, and we want to be able to see in the electromagnetic spectrum. That's NATO open doctrine of electronic warfare. If I just highlight how we feel about the electromagnetic spectrum, we don't think we'll dominate the electromagnetic spectrum again in warfare. We need to have freedom to operate. We're not expecting that the spectrum will be empty or not contested, but we're going to need to be able to fight our way through that fog. So what's this one about? This is about the idea that we need to have electronic surveillance to visualize and understand. We need to be able to find emitters. We need to assess them. And we will be doing electronic attack. There is a big focus for us on attacking with energy in the electromagnetic spectrum. We need to be able to degrade the enemy performance. The opposite is also true, that if people are going to be attacking with energy, we need to be able to protect ourselves from enemy electronic attack. So what does that mean in reality? I'll try and take you through this little top right picture. We are imagining that if we wanted to have freedom of action in a contested airspace, we will be flying in with aircraft, not necessarily the one on the screen because it's not ours, the British. We would be flying in with aircraft, and we might be going against the most sophisticated modern radars that could be agile or non-agile radars. There could be all sorts of other transmitters, and we want to go into that area, jam, attack, and adapt so that our aircraft, if I'm frank, can go in and get out and do what they need to be there. So what we need to be able to do is to go against the most sophisticated future emitters that could be in different frequency bands at different moments, hopping all over the place with different bandwidths and really completely unpredictable. Probably not completely unpredictable. One of the key things that we need to do is to adapt and learn. So the key words in here for me is that we need to include the ability to learn on the mission. We need to assume that when we've taken off, although we knew what the threat was, it will be different. We need to be able to sense what's going on in the battle space. We need to be able to automatically update what are we doing so that we know where the electromagnetic energy is and where we need to put our energy. If we do this right, we're calling it cognitive EW and working with many people on that. That will give us the ability to understand the environment. It will give us the opportunity to fight in the environment and to attack these modern radar threats that are absolutely key for our freedom of action. And I think one of the key things that I was asking people yesterday is that learning. So although we can do power minimization and other things, I want to know how we can carry that data set from mission to mission. So when we talk about kind of, I saw yesterday kind of optimization techniques and how to adapt beams and such like. It's like, how do you actually learn that from this mission to take it into the next mission, and how do you move that knowledge around your aircraft to actually be able to reconfigure antennas, energy, or whatever? Because although it's interesting to just adapt on the fly to the energy that you receive on your antenna, that's probably not optimum, frankly. You should learn. So although I know that, covariance inversion, whatever, is great, and that can tell you from the current, ideas like knowledge aided or what occurred before is absolutely critical, frankly, and why wouldn't we? And this will let us, this mission for us is to maintain our ability to really penetrate defended areas, so we can have freedom to maneuver. So, moving on to another challenge. I'm still going through the challenges of that contested future environment. This is the kind of thing that we're trying to do to start looking inside buildings. I want to know what's inside buildings. Probably what I want is much more than I'll get. But what we've been doing, and we're doing a lot on, is through building imaging. So we can do RF sensors on the other side of walls and all that kind of thing. We all know that. There's a lot of mature products by different companies. But what I want to be able to do is to be standing off at long range or very long range and to see inside buildings. And I think it plays to things like Richard's poster yesterday that was looking at electrical devices to work out what's inside buildings. But we want to know really everything that's going on inside a building. So what we're doing about that, working with Cranfield and others, we've been investing in collecting data sets, low frequency SAR data sets. And I guess what can we see here? We can see it's early days would be my impression, because we got what looks like, except for some weird bins, a benign room with one of those classic science trihedrals in there to make a really high signal. And we're trying to work out if you can actually see that through the walls. And I'd say it's promising. I think the thing that's absolutely key for us is that we think we've seen enough in results like this and other ones that we're investing heavily to continue work like this on low frequency penetrating sensors. One of the things, though, that I also want to highlight about that when we're looking at signal processing algorithms is you might not be able to collect all that data you want. The idea of flying around the target or getting all the frequencies you want or getting to use the RF spectrum where you want to, that's probably nonsense in my military world. You're only going to get to illuminate and turn on with a limited time from a limited range of angles. So what we're trying to do is to work out what is the minimum amount of data you need to collect across frequency and angle to actually be able to do this. So one of the things we've been doing working with Airbus and others is we've got the Bright Sapphire 2 UK radar system that's collected some unique data sets, and we're going to be distributing those. That's an advert, if you like, to USAR 2018, but we're going to be distributing that data set. So we were talking, I think, yesterday about open data sets to say how can we process that low frequency complete data dome, we'd call it, wide frequency, all angles, and how can we process that with the minimum amounts of pieces of data to actually get what we want militarily? Because once we understand that, we can then talk to our RAF or whoever colleagues to actually go and collect the right amount of data rather than imagine that we're ever going to fly all the way around the target and at multiple angles, which we just won't have time to do. Another headline, if you like, UAVs sometimes are really opportunist, so working in collaboration with a number of people, but including Kinetic. We're looking at the idea of SAR and other ways of doing remote intelligence where you might have multiple low-frequency radars or other sensors on UAVs flying around buildings. And we're doing different proofs of concept at the moment where we want to see and image all the structure inside those buildings. And that's carrying on, and an absolutely key real-world challenging problem, much harder than, I'll just pick on that, see an aircraft in the air again example. What else are we trying to do, though, in distributed, difficult worlds? This is a real problem area. We want to be able to see, and we're working with other nations and have been in the last month or so in Australia, we want to be able to do all sorts of all sorts of sensing aided by signal processing in the really difficult urban environment. We want to be able to see behind buildings, inside buildings. We want to understand what's going on. We want to be able to find future communications emitters or otherwise of all sorts of different styles, MIMO, we're talking 5G, all sorts of things yesterday. But we need to be able to dominate that in the most difficult environments, and we need to exploit all those degrees of freedom. Probably won't unpack that anymore, but that's going to be a very difficult problem. the kind of testing of that we are doing, what's the things I can point to? We're looking at signal processing for distributed arrays. We're looking at the things we've got here, non-line of sight propagation. So that's absolutely key for seeing around the corners and to understand that multipath environment. And I think key military benefits, but there's going to be a lot of things that we need to do, I guess. There's no key new messages here, apart from the fact that we need to be working on sustaining what we might have been used to being able to do in electronic surveillance or electronic warfare in more open environments into the modern difficult one where they might not have turned off many of these other transmitters, and there's lots of things going on. Let's change modes again. I've been picking on RF. I started in radar in my career. Maybe that's where I started on electronic surveillance today. We're looking at many different challenges in imaging through obscurance. We can start off with that helicopter in the top right picture. Yeah, we do land, and it's quite difficult, and you damage things, and you break aircraft, or you break different things. But what we really need to be able to do is we need to pilot in impaired areas, and we need also to see through annoying things like cloud, and we need to be able to see through dust clouds and all sorts of other things. So what we're looking at is to be able to do single photon LiDAR, where you just be able to get single photons through at a time. We're looking at all sorts of things like lasers to maybe help make gaps in the obscurance. And we're looking at different ways of actually doing single photon counting. So got some examples here. They're grateful for permission to use these. So on the left-hand side, we're looking at the ability to image people by doing single photon measurements of their faces. And we're looking at the fact that you can then do depth profiles and get far more information. There's a lot of signal processing going to be required to take something like that is in early days to be able to get to the level that we want to be able to do. Signal processing on the right, we're looking at the ability to be able to do that collection. But here I'm picking on the parameter, I guess, of time. And this is the fact that you might not be able to dwell for as long as you wanted or to be able to see. So I think one of the critical things we should all look at when we look at different results is what's the time requirement on this? How long do we have for that missile engagement or to loiter, or how long will this person be out in the open for us to actually be able to see them? So time's absolutely critical that we need to drive down. So moving on from the EO seeing for obscurance, I wanted to touch on a subject that's often not brought out into the open because it's very sensitive, but I need to touch on electronic protection measures. The platforms or the sensors or the systems that you often talk about or you might see great pictures of can be damaged, attacked, blinded, obscured really quite easily, in my opinion. So what we're talking about here is the use of the spectrum is increasingly congested. We're using that word again. We also jam each other, which is a bit unfortunate whenever we work in a coalition, but we should admit that. So there's challenges there. We need to look at how countermeasures can be created that enable us to survive being attacked, but also we do want to attack other people as well. So both of these play both ways round. So we want to be able to survive when people are jamming us, when they're blinding us. Subjects that we've not talked about much in this conference, but counter-ISR, counter-surveillance, counter-sensing, the injection of subtle signals. So we need to be able to get to the point where we can survive being confused and overloaded. We need to be able to have sensors that have the built-in hardware, built-in signal processing that can actually survive this interference. And by survive, I both do mean hardware, that we don't just break all our systems, but I also do mean that we can still do our mission. So we are thinking about different approaches. Often they end up classified, but we're thinking about different approaches, and we list some of them here, kind of simple things like changing detection algorithms, changing the number of spatial channels, changing the way that we're doing all that clever beamforming to not let it be seduced. I'm also, I see many of the things everyone's talking about as opportunities and threats. So I think I was talking to Mike yesterday, as soon as anyone says machine learning or anything like that, I'm like excited because I just stick the word in front of it of counter. How can I take that on and how can we trick that? But this is going to be a really interesting area for us in the military to have the performance we need. So I've given you hopefully a rich, if not fast tour of some of the areas that we've been doing. I think I just wanted to point to the future in a little bit. with one slide. And what I wanted to do in the slide, and I think the tabulation went wrong, the UDRC was meant to be on the next line down. So this was about novel S&T approaches. What do I want to point to? It's a little bit small on the font, but it's giving you some ideas on the left. So we are obviously looking forward to continuing within the current UDRC and carrying on. UDRC as a way of working is absolutely key to us in mod. It's something I talk to my seniors about, and it's absolutely critical that we can connect your thinking into our problems. Some of the things that we're thinking about in the future is words we all use, large data sets or multi-dimensional data sets. It's trying to find what we need to find, the kind of, in that multi-dimensional, what do we use here? We're using the word haystack, but how can we find what we actually need to find in that massive data? How can we look at different ways of doing that? And we talk about correlations, we talk about what is the information content. And I think that's absolutely key, is to go back to the word information. I need to get to the information that's in the data. I also need to get to the point where we don't have embarrassments, where we did have the data, but we didn't form the information and we didn't form the intelligence, because that happens. And we've heard it in the news, in the public in the last week. We need to get into that high volume. We're going to have sensors. You imagine if that picture I showed of the UAVs, we're going to have more data flowing in different ways, and we heard of that yesterday with the Ajax vehicle. Otherwise, how can we actually deal with that data? How can we look at things that are changing? How can we look at how we process it? How can we look at tasking those systems in a different way? How can we be assured? How can we trust what we are getting out of those? Because one of the things is that if we're going to take action against this data under rules of engagement or fire, legal, we need to know why. We need to know why it was the right thing. And we talked a bit about the information age. And we talked about how fast we've been in defence to respond to the information age. We are accelerating in different ways. I'd probably say not well enough in many, but we need to be going a lot quicker. And I think we need to know that we're not going to be just about big platform, large sensors. It's going to be about all sorts of different sensors. It's going to be about actually transporting, we heard it yesterday when we were talking comms for a moment, getting the right information to the right decision maker in the right timely way is absolutely critical. For me, though, I always like to wind the military up, because I don't think they always need the picture or the live video to be fed all the way to the senior who wants to make the decision. They might actually have to deal with an insured intelligence product instead. So there is going to be a lot to do there. I think one of the other things, though, and I'm going to go back to it, and if anyone's ever spoken to me, I go on about open standards, open architectures. I think one of the key things that we need to be doing is, within some of our future signal processing, is to be thinking about how this framework that we're setting up to be the open source framework will allow us to bring algorithms and data and sensor models to be doing things like the tracking and the state estimation, where we can be taking different people's proprietary or different models and to be plugging that in. Because what I want to do is to find and quickly exploit the best algorithms to get them into the key data sets that actually make a difference. So, going back to my starting premise, and I think we're going to have time for that question, so that's good. Information generator. For me, signal processing is about the information generator. That's why I need you to do it. We need to keep the lights on. We need to generate the information. We need it to make our decisions in MOD, and we need to make them well, and we need to make them timely. We do need to collect data. We need to be able to collect that data whilst fighting in a contested and in congested environment. But we also need the signal processing to take that data forward, and we need it in a number of key areas. I think the other thing I'd add there is overmatch. I don't just want our signal processing and our sensors to be as good as expected. I want them to be better than the enemy's, because I need to see from further, and I need to see sooner and quicker with better decisions. So although we talk in the open about a lot of our techniques, we need to be not behind. We don't need to be just as good as open literature. We need to be exploiting and getting ahead. That is the vision for what we need. And I think the key thing for me is a message from me to you. The MOD needs access to the world-class ideas, algorithms, technology, and we need to be working together to do that, to actually get those ideas tried and tested in the relevant environments that we work in and we need. So I'm absolutely key for all the academics as well as DSTL to make that happen. So that's it. slightly quicker than I probably thought it was going to be. I should thank my DSTL colleagues, both those listed here, and I thank those who've come this week, because I think one of the things I see as a key challenge is to bridge the gap between academia and military, and I think DSTL really helped with that, so thank you.